Let's try involving polar coordinates. For this problem, we have suitcases of mass m, which start at rest, and they're sliding down a curved chute of radius r and exiting the bottom. And we're asked to find Fn and theta dot for this event. So our standard method is to first draw a free body diagram and then apply Newton's second law to solve the problem. So if we come over to here, we have mg acting straight down. We have a normal force acting towards the center of the curve. And if we want to track out where theta is, if theta is here, this angle would also be theta. And that would make, by alternating angles, these are all 90s in here, that would make this theta as well. And from there we can break our mg up into components. So our system that we'll use, that's r hat, and this is theta hat. Recall that theta is in the direction, theta hat's in the direction of increasing angle, right? And by the positive right-hand rule, that's the direction it would push. So that's what we're going to call our positive theta hat direction. So from there, we'll get an mg sine theta in this direction, and an mg cos of theta in the theta hat direction, and we won't need this mg anymore. So there's our free body diagram. If we had friction, it would be acting up the inclined plane, but we don't have any. And you'll see in another example why that's a good thing in this case. So let's apply our equations of motion. So sum of the forces in the r is MAR, and sum of the forces in the theta is MA theta. So in the positive r direction, we have mg sine theta minus Fn equals m r double dot minus r theta dot squared, which we got from our polar analysis. And then in the theta hat direction, in the positive theta, we have mg cos of theta, and that's equal to m. And recall that this was 2r dot theta dot plus r theta double dot. Okay. Now, one simplification that we can make is if we assume that r is a constant, then r dot is 0 and r double dot is 0, which allows us to cross these off. So one of the things we're after is Fn. So if we rearrange that, we would get Fn is mg sine theta minus plus and the m r theta dot squared, which that's a variable. If we come over to here, the m's clean out, and we get g cos of theta is r theta double dot, of which that's a variable, as is that. So this right here is a second order ordinary differential equation. And one very nice technique that we can use to solve it is that we can convert this right here. So if we take a look at that, theta double dot by definition would be d theta dot dt, right? The dots imply that it's a time derivative. Now we can convert this by multiplying and dividing by d theta, which is numerically equal to 1. And the benefit to doing that is it will turn it into, this is theta dot by definition, so this becomes theta dot d theta dot d theta. So we converted it out of a time frame and into a rotating theta value, which is very useful for addressing that. So we get g cosine theta is equal to r theta dot d theta dot d theta. If we bring the d theta up, we can integrate both sides of this, and this will give us g sine theta is equal to r theta dot squared on 2 plus c1, our constant of integration. Now the boundary conditions were at theta equal to 0, that started from rest, so theta dot, the sweep rate, be 0, so sine of 0 is 0, theta dot is 0, that leaves us with c1 as 0. So with that we have a value for theta dot squared of 2g sine theta on r, of which we can take the square root, and that's one of our answers. The velocity will be r theta dot. It's an r omega type, so it'll be square root of 2g sine theta on r, and this r can come in here as an r squared, which will clean out, and we'll get our answer as the square root of 2gr sine of theta. The other nice thing about having this is it solves for that variable. So if we use that, Fn will be mg sine theta plus mr. Now theta dot squared, bring the radical back over, is 2g sine theta on r, at which point the r's drop out. And note that we have 2g sine theta, another mg sine theta, so Fn will be 3 mg sine theta. So with that, we have the velocity and the normal. So Fn max will occur at 90 degrees, and it'll be 3 mg, and V max at the bottom will be the square root of 2gr. Now, there was sort of a cute way that we could have done to check this. If we think of it from pure conservation of energy, the energy at the top is mgh top plus 1/2 mv top squared, of which it's not moving yet. And the energy at the bottom is mgh bottom 1/2 mv bottom squared. And we're at the bottom down here at h equal to 0. And without friction, these are equal to each other. So we can say then that energy at the top has to equal the energy at the bottom. It's conserved. And we get mgh is equal to 1/2 mv bottom squared. The m's drop out. And we get v bottom is the square root of 2gh. In fact, we could have done this for any h. Because h, or delta h if you'd like to call it that, would be r sine theta. That's theta, and that's r, that's our drop height. So if we replace this h with the square root of 2gr sine theta, we get the same answer from above. And it's interesting that it's 3 times the weight. In fact, you could think of it as 2 parts. There's an mg, which would be your static, plus a 2mg, which is your dynamic, and that's due to the acceleration, the centripetal acceleration, and this is just your free body diagram at rest, normal force, holding it up. And that's always there, and this is a function of the speed. Recall that would be v squared on r, or r omega squared. So it's interesting to see where the 3 mg is coming from when we look at it. So an application using polar coordinates.